Hello, right, here's another couple of magnetic field questions. We're starting off here with defining magnetic flux. Right, so not to be confused with magnetic flux density or magnetic flux linkage. So let's contextualize it first because a magnetic flux exists through a surface. So let's say magnetic flux through a surface, which will give us something to pin the rest of the answer around. And we can say that that is equal to the magnetic flux density, perpendicular or normal, whatever you want to say. Let's go perpendicular, which I'll do in shorthand, to that surface multiplied by the surface area. So sort of made this surface centric in the definition. You know, we can put the trig in anyway. You could take the surface area that's normal to the magnetic field, but yeah, just pinning everything around the surface I find easier for the definition. So magnetic flux through a surface, and then the magnetic flux density perpendicular to that surface, and then multiplied by the surface area. It's a nice consistent definition then. Right, part B, figure 4.1 shows a solenoid connected to a battery and the magnetic field through it when the switch S is closed. Right, the battery has an EMF of 24 volts. Yep, they've told us that. Negligible internal resistance, fine. Solenoid is made from copper wire with radius of that, length of that, and resistivity of that. Right, calculate the current in the solenoid. So we've got that the current is the potential difference between divided by the resistance. We also know that the resistance is the resistivity multiplied by the length divided by the area. So our current is going to be V times A divided by rho multiplied by L, which is 24 multiplied by 4.6 squared times 10 to the minus 8 times pi. That's our cross-sectional area. Then divide by the resistivity, 1.7 times 10 to the minus 8. So they're going to cancel. And the length, 130. Right, okay, so that simplifies things somewhat by getting rid of 10 to the minus 8s, make it easier to type everything in. And we get 7.219, so let's say 7.2 amps to two significant figures. Right, that was fine. I assume the magnetic bit's coming up now. Tiny electrical spark is created between the contacts of the switch S as it is opened. The spark is produced because an EMF is induced across the ends of the solenoid by the collapse of the magnetic flux linked with the solenoid. Yes. So, you know, we flick the switch, the current stops, which means our magnetic field is going to disappear. So as that magnetic field is dropping down to not existing, down to a flux density of 0, we're going to get a change in flux linkage, which means we're going to get an induced EMF. So what have they given us here? They've given us the initial flux density, the number of turns on the solenoid, the cross-sectional area, and the induced EMF. And they want us to give the time taken for the magnetic flux to collapse to 0. Right, okay, so our induced EMF is proportional to our rate of change of flux linkage. All of this is perpendicular, isn't it, with all of this? We've got our flux density multiplied by our cross-sectional area multiplied by our number of turns. That is our flux linkage, which is changing in some time delta t. And I mean, this is going to be our delta, our change in flux linkage, because B is just dropping down to 0. So this is going to be our maximum. It's only B that's changing. So we're going from our initial magnetic flux density down to 0. So that value of BAN is going to be our change in flux linkage. Now the equals, to turn this into an equation, you know, we've got Lenz's law, we're putting in a minus sign. Sometimes this can throw people. But we know that delta t has got to be positive. So we're saying that delta t is going to be equal to the magnitude of BAN over epsilon. Yeah, okay, if we put in an equals and then a minus 1 as the constant of proportionality there, That's just really saying that we've got a negative induced EMF, and then those two minus signs are going to cancel. But we know we're going to have a positive time. We know this. We're not going backwards in time when we flick the switch open. This ain't Back to the Future, so we're going to be getting a positive delta T. So this is going to be 0.09 times 1.3 times 10 to the minus 3. Then what have we got? We've got the 1100 turns, and we're dividing that by 150, which is definitely going to go at the calculator, and we get, what are we getting? 8.58 times 10 to the minus 4. So 8.6 times 10 to the minus 4 seconds. Right, so that was nice. Is that the end of that one? It was fairly short, but it is the end of that one. Right, so figure 2.1 shows the circular track of an electron moving in a uniform magnetic field. Yeah, there's the track of the electron, 24 centimeter radius. All right, okay, it's going to annihilate somewhere over here, but let's get to that in a moment. The magnetic field is perpendicular to the plane of the figure. Speed of the electron is 6 times 10 to the 7 meters per second, and then we've got the radius that they put in the picture. At point B, the electron interacts with a stationary positron. Right, so we're going to get some annihilation later on. On figure 2.1, draw an arrow to show the force acting on the electron when at point A, labelled as arrow F. Well, it must be our centripetal force, so that is going to be going towards the centre of the circle. Label it F. Explain why this force does not change the speed of the electron. Well, we've had this sort of thing many times before. So we'll say F is perpendicular to the direction of motion. Therefore, it does no work. Therefore, no work done on the electron. So put that into a fully written out sentence and you'll be fine. Calculate the magnitude of the force F acting on the electron due to the magnetic field when it is at A. So F is going to be equal to mv squared over r. That's fine. So what have we got? We've got, this is just an electron, isn't it? So 9.11 times 10 to the minus 31 multiplied by, well, let's just square that straight out. So 36 times 10 to the 14 when we square v, divided by 0.24, which is giving 1.3665 times 10 to the minus 14, so 1.4 times 10 to the minus 14 newtons, two significant figures. Calculate the, that's what I've just done. Calculate the magnetic flux density of the magnetic field. Right, so this is also going to be equal to BEV. So B is going to be equal to this F that we've just worked out, 1.3665 times 10 to the minus 14, divided by E times V. So 1.6 times 10 to the minus 19, multiplied by 6 times 10 to the 7. So B comes out as 0.001423. So 1.4 times 10 to the minus 3 Tesla. At point B, the electron and the positron annihilate each other. Yep. Positron has a positive charge, same mass as an electron. Particles create 2 gamma ray photons, so they can conserve momentum. That's why you're getting 2 of them. And calculate the wavelength of the gamma rays, assuming the kinetic energy of the electron is negative. So we're just doing a mass energy into photons on this. So we've got 2 mc squareds that go into 2 hfs. So we can cancel those. So each one, so an mc squared for our electron is going to go to an hf, which of course is an hc over lambda. So 1 electron to 1 photon, you could, same as 1 positron to 1 photon. So that's why we don't have to worry about the mass of both of the positron and the electron. So we can cancel one of the c's, and we're trying to work out what we're trying to get wavelength, aren't we? So wavelength is therefore going to be equal to Planck's constant divided by m times c. So 6.63 times 10 to the minus 34 divided by the mass of the electron, 9.11 times 10 to the minus 31, multiplied by 3 times 10 to the 8 for the speed of light. So that gives a 2.4259 times 10 to the minus 12, which is 2.4 times 10 to the minus 12 meters. So yeah, just mixing in with going back to our days on particle physics there, keeping us on our toes. So yeah, two quick ones there. Heavy on the calculators, that one.